lets us, this helps us rethink how we can think about cities, urban spaces as a dynamic and ever-changing cityscape rather than a static one-person perspective design process that we've latched on for centuries. So that wraps up the disciplinary potential. Then what are some of the professional potential here? And I'm sure you guys have seen a lot of the generative design tools emerging in the field in recent decades. This is one example, Finch 3D. By dynamically changing the floor plan, this lets you see some of the configuration of the plan in real time. And this is a short instruction by Autodesk explaining what generative design tools can do. And this uses a combination of traditional optimization methods and some of the more machine learning or AI enabled methods to scope and understand the design space holistically using rigorous data scientific methods. So then what this really enables us designers to see and assert values in is that design options actually do have a positive, significant impact for the occupants and the end users of the buildings. So with these type of tools, not only can we make it clear that certain design options have real impact and real consequences in the eyes of non-practitioners, so someone who's not architecturally trained, but also that we have the agency to curate and really create the kinds of space that we are that we've been trained to create with these kind of tools. So with that said, I took a deep dive into what kind of landscape we're currently facing with these emergent tools of computational geometry. So what you see on the what you see on the x-axis is the medium, going from language to image 2D to image series to 0.5D, and then 3D objects to moving objects to information, which we can regard as higher dimension. And then there are different tasks that are often explored within computational geometry, going from detection to segmentation to synthesis and generation. So I think you guys are exploring probably like 2D to 3D in this generation and synthesis space. But what I want to try to get at from this is that this is a really big technological drive of the century that's going to impact and shape a lot of the practice that we do with images, sequence of images, as well as 3D objects, which all of which architecture regards. And I think this graph everyone has seen so many times, and this kind of emergence of the rise of AI and ML tools were made possible in the last decade because of the three main forces. First, the increase in processing power, as well as decrease in cost of data storage, and exponential data growth since 2010, enabled by diffusion of personal devices and technologies that enable us to gather data, store data more efficiently and at a low cost. So, and buildings are everywhere, spaces everywhere, and these are the main vehicles by which human activities are enabled. So what I'd like to propose in this sequence of projects to come is how can we rethink the process of data-driven design away from building information management? I mean, not away, but like how can we evolve from BIM to really capturing the performance and usage of space by humans. So can we make it into a socio-spatial data science process? And for that, with that in mind, I'd like to propose this framework that I've been using in thinking and configuring these types of projects. So there are always three parts you will be dealing with. First, data, second, model, and then the third one, project. So by walking you through some of the more experimental projects I've conducted at the GSD, I'd like to show you and walk you through the project process there. So first project I'd like to introduce is Beaux-Arts hyperdimensional cartography. And this one, we used 2D GANs, so DC GANs and style GANs, and in a cultural spatial archives, meaning we created a custom data set of Beaux-Arts drawings from historical archives to understand this design space of Beaux-Arts drawings and Beaux-Arts style of architecture. So I'll let this play. We came up with a novel visualization method to project hyperdimensional space of the Beaux-Arts drawings. So this is the projection method and data visualization method we invented in the process. And on the right side is the navigation of that latent space of the Beaux-Arts drawings. And this project started with the data, very intense data mining process, encompassing 5 different Beaux-Arts drawing archives and historical databases to come up with the sections, elevations, and plan drawings of Beaux-Arts. And if I zoom into some snippets of these, there were some data processing involved to augment the data set to really let the unsupervised learning of 2D GAN be leveraged with a larger sets of data. So if the aspect ratio of the drawing was long, then we would take a section of it by cropping it into a square ratio that you guys are familiar with as necessary for training of these GAN networks. And there's always a question of like, how do you make sense of this data? What is visible to humans? What is visible to machines that are not yet visible to humans? So there are ready-made tools such as TensorBoard and the embedding projector, which helps you navigate these high dimensional space through dimensionality reduction algorithms such as UMAP, TSNE, PCA, and you can also use like different kinds of like custom algorithms. So what this does is, so there are certain latent information or embeddings that are visible after training in the latent space that we currently don't see, and these help us navigate that space. One caveat with this data set is that this isn't like handwritten digit kind of data set where human eyes can easily cluster and differentiate like one data point from another. So I think even running this, we're not really able to see why certain data points are clustered in certain ways and why we're not. So there's no visible pattern we can observe from this kind of mapping. So this idea and issue of mappability, I'm sorry, I think I might have pressed something. Can you see my screen all right? I just exit the full screen. Yeah. Yeah. So this issue of mappability and navigability in large kinds of like visual data sets becomes it remains an unresolved issue. So that's an area of investigation if anyone's interested in more of the data side of this process. And then the next step is, of course, training a neural net. Here we used DCGAN. On the left, you see the plan data being trained and generated as a validation. And on the right side, elevation sections are being trained. And another part of this is being able to map these generated results as with the data set itself. So as I've said, I'd like to reiterate this difficulty in generative modeling, where there isn't a clear path to assess the similarity and results. So we have mapped this onto 2D plane with the dimensionality reduction algorithms, but there isn't a clear rationale we can observe why certain data sets are close to one another and why this mapping is happening in 2D space. So this resulted in this kind of exploration where we're walking through latent space, but with a very particular and intentional projection methods. So each of these like wedges are created between two specific latent points in the space. So we do see these smooth interpolation between vectors. However, with these nodes and lines, we can easily observe where the actual like data points are in relation to the interpolated points. So, and this is a diagrammatic explanation of how we are projecting this high dimensional space onto 2D plane so that humans can navigate these large data sets and trained by neural nets. So I'd like to make a quick note on this framework of working with data, collecting data, cleaning, and then being able to leverage that and understand and make sense of that data set through models. And in this case, this was DCGAN. And I'd like to add another dimension to that. So project can be thought of as so what of this process. So you have all this data, so you were able to train successfully with the neural network of your choice, then what does it really accomplish? And in my case, in this project's case, this was to serve and enhance the navigability of these data sets and increase our understanding of how we navigate this latent space created by tens and thousands, 10,000 or so drawings from specific historical architectural style. Likewise, automatic affinities. This is a project that I did as a thesis of my MArch-1 program, leveraging 3D GAN and urban block design. So leveraging these generative modeling tools and networks, I was able to test out the feasibility of 3D GAN around 2019, and this was a 3D GAN paper and code I used from MIT CSAIL that came out in 2016. So they were, I think that was like one of the first like forerunners of the 3D GAN network that came out of the computer science research. I saw it and it was just incredible to see neural nets learning shape distribution in some ways. There was this like perverted like mathematical idea to me in that there is this inherent distribution that could represent, for example, like a chair, like a commonplace object such as chair. And so here there's I use the 3D ShapeNet, which has, I think, about 20 categories of 3D objects. And in this case, I used chair as my main study object. And using this 3D GAN published by MIT CSAIL, I was able to train a 3D GAN network. So here you're seeing the training process of the chairs. So after around, I think like 3,000 or so, you can start to observe discernible like shapes of a chair that start to emerge. And this resulted in some interesting shapes from a designer point of view that human designers would never make. So these have uncanny qualities that are unfunctional sometimes and additive and redundant, and really capturing this logic of a machine. So you're learning the distribution of these like large space and trying to emulate what you've seen through these generations. So in my project, I wanted to apply this in urban context. And that decision was actually guided by availability of building data as well, because there wasn't a granular level of data available at the time. And I think it's still an ongoing challenge. And the easiest data set I had access to was the urban block shape of Manhattan. So I came up with these like 5 steps to use 3D GAN to come up with a methodology to create new urban block leveraged by 3D GAN network. So first was I was able to scan through New York City website that had a really good 3D building block data, and collected volume data as well as image collection of the facade. And as you can see, they're not all from New York. So one aspect of this project was to be able to combine different like styles and origins of the image with the volume that I'm collecting in this 3D data. So on the left, what you see is a training in progress based on these New York City blocks, and on the right is generation results at a point at a training epoch that I thought was optimal to use. And as you can see, this is not by any means realistic or complete. And that's another ongoing challenge of these again models to this is an ongoing problem of 3D GANs. Like it's not complete, and also there is no such thing as like really optimal convergence that can optimally capture the real data set. So I think that leaves actually interesting quest for experimental creative designers like us to really leverage and like come up with a system to interpret these results. So what I did in this was, so I had these original image of facades, and I was able to use computational infill, image and painting algorithms to shake up these new existing facades into kind of this, let's say like disordered array of the grid. And I used some methods of like z-depth mapping to really like make sense of these like 3D data, and played with the resolution of the voxels to create a kind of new aesthetic of an urban block. So this is a kind of a compositional process I used to map the facade onto that volume. So the project became this site where from these like data sets I've collected, I wanted to create new kinds of urban block across from the Hudson River in Long Island City. So these are some of the results that came out of the process. And I'd like to just emphasize that this is just like 3 archetypical styles that I've like identified out of like, I don't know, tens and thousands of like combinations that were possible out of this process I made. So these are some of the results of like facade and volume distribution. And as you can see, I use exactly the same like facade composition in 3 different ways of 3 different types of 3D shape volume distribution. And these kinds of like different grid system were possible because of the voxel resolution fine-tuning step I had in the pre-processing of the 3D GAN data. And these are some of the aesthetics that came out of this process. And you see the structural grid is actually reflective of the voxel resolution I was playing with, and as well as the match and mismatch between the facade grid and then the structural grid. All this is an interior views in one of these permutations of the buildings, as well as exterior views and zoom ins. So I'd like to reflect on this process in 2 ways. So I had a project definition of why am I doing this, and like what like methods I'm using. And then the second part is being able to really leverage that 3D GAN training for your purpose. So these are these often like the shapes that come out of the 3D GAN training are not yet sophisticated to be put directly into an architectural design proposal or any other type of like design just yet. So I think this second part of like actually establishing the pipeline of how you're going to train and what you're going to do with the training results is actually pretty critical in like shaping the end results of your design. So I'd say be deliberate about kind of the purpose of your project and tailor your pipeline for that purpose. So in a way, if I had this like chair data and then the model was 3D GAN, this process for me was to examine feasibility for 3D GAN of urban blocks. And this process itself for me, I had the data sets and then the models trained and then like computational pipeline. And for me, it was to explore new aesthetics of urban figures that arise out of trained 3D neural nets. And also this was a case of an experimentation from my point of view to think about how to integrate machine learning in design process through data curation, model curation, and presentation and processing of these intermediate results. So those are 2 projects that I wanted to share with you today. I'm going to pause here and just ask any clarification, take any clarification questions, and any other types of comments. Okay, if I don't see any question, I'm gonna move into the reflections in this process. So after that 3D GAN process, I have continued exploring with different types of 3D shape representation learning. So 3D GAN is a kind of a nickname for this like one network that MIT CSAIL group came up with in 2016. And like after that, there are just like tons and tons of like new models that come out like every day. So this area of study, 3D shape representation learning, is what I'm like continuing to be fascinated by and been exploring the potential of at the GSD. So one project I've done with George and Dong-Yoon here, who worked as research assistants, is this not GAN project, where we use a different kind of network and these different kinds of data sets, which is actually custom generated, to map the latent space and latent walk of these hybrid knot surfaces that we created. So in the middle is the latent walk you're seeing, and then on the right is like the kind of data points. These are, I think, the actual train data of the hybrid knot surfaces, and on the left is you see the latent space mapping, the same methods that I described earlier, and then the topological information of the void and then the shape itself. So what is it? What does it do? So we wanted to explore these type of like knot surfaces, also called ciphered surface. And the characteristic of these surfaces is that it's non-orientable. So if you have a solid like this, it's orientable, it's analytically describable. But if you have these non-orientable surfaces like a knot or the like Klein bottle is another example, it's hard to really describe analytically, and that inability to describe analytically provides actually a really good reason to use empirical approach, meaning like such as deep learning methods. But without going too much into the details, I'd like to share a reflection on that process in terms of data and then model. Dealing with 3D data, it poses very specific set of challenges because representing 3D data has so many different ways that are being used. So unlike images, we know like it's RGB, you have like pretty much like 3 sets of like matrix that represents an image. 3D shapes can be represented in like so many different ways. So those are some of the challenges that you'll face in 3D GAN training process. And on the model side, there's a new model that comes out like almost every day. So there will be some challenges, but actually more exciting opportunities like navigating what's possible. So first is, I think, data capture, and in specifically regarding, I think, like architectural or urban context in the built environment. How do you make sense of the world as it is now with the tools that are available for us? Of course, we have like elaborate BIM models, but first it's proprietary, and second, it has maybe like too many levels of details. And third, it's hard to acquire at scale. So like one, I think, popular method that's been used a lot these days is just LiDAR capture of the urban context, which we are seeing a lot in like real estate context, or also architectural and engineering context of just like going in with like a LiDAR scanner, scan the interior, then you can capture the building as it is now. And then for us, I think there's another issue of like data representation. So for example, like this type of like LiDAR data data would come in as unstructured, just point clouds. So you just get like coordinates of like, I don't know, like 1 million points. And then how do you make sense of that is a second part of the question. So so there are like non-Euclidean data of point clouds and graphs and meshes. So these are some like data types that we've been explicitly and implicitly been working with as designers. But also there's a structured data with descriptors or projections. So I think it's a topographic information of like 2.5D images are one way to approximate these like 3D information, or depth map, which is a similar kind of concept. And you can approach it volumetrically by going about voxels or octree. And in the 3D GAN project I shared with you, I took the voxel approach because it's the easiest to matricize a shape into a certain resolution grid of a voxel. Or you can take like multiple views of the same object and work with 2D rather than 3D. And in the process of the nut surface GAN, not GAN, that I was working with, I actually used Grasshopper to generate like these data sets. So we use a certain enumerative logic to make a lot of these hybrid surfaces and created our own data sets to explore this hybrid knot surface collection. And we used a custom script from Andrew with a professor I work with at the lab. And this type of data also presents the same kind of challenges I just explained. How are you going to capture these? Like, is this a mesh? Is this a point cloud? Is this a voxel? I think that's a question Dong-Yoon, George, and I've been like struggling a lot with, and we came up with like ways to represent it or be able to feed it into the neural nets in certain ways. So it takes a lot of like processing of the data to really capture 3D information. And so that's a mesh representation of one data point in that hybrid knot surface collection. And then this is point cloud, just voxelized point representation of the same surface. And so with one surface, because this was non-orientable, meaning it was like a thin mesh, we needed to thicken it. And that posed a lot of like challenges in terms of like, is this a valid data? Is this not? And there are like various ways to represent the same thickened mesh. First is we can calculate like random 200,000 points, and then the distance function there. So this is kind of capturing in terms of like point clouds. So we're sampling like random points and assigning distance value there. Or we can represent as a mesh or voxel, and then this is rendered using Marching Cube. But as you can see, this is the middle one is 128 resolution and the bottom is 32. Then we see a lot of these actual 3D information being lost at certain point. But working with 128 cube is just way harder than working with 32 cube of data. So it's a fine line between having enough information, but not too much to crash your computing process. But of course, if you're like really loaded with computing resources, like you're like one of the GPU makers, you don't have to worry about these. But I think as an individual researcher and designer, this becomes an actually significant point of consideration. This is a zoom in of the different data processing types. And of course, going back to this project, this is just a really abstracted representation of the real life data of New York City blocks. And there are must be many other better ways to improve this data collection and processing part of the project. And moving on, this is also the same type of process, but this data set was collected by our own George here, and we're exploring the latent space of these classical busts and trying to map the latent space of that data set and doing a latent walk based on the trained data that you see on the right. And again, we're analyzing the topological information on the left side as well. And this one's the same shape GAN, but with the tree root data. So there are just a lot of crowdsourced data of these like real life objects, and we trained a variational autoencoder to learn the distribution of the trained data set. So, and that brings me the question of choice of model. So I went from using 3D GAN, which was like a very early type of 3D shape representation network, to using shape GAN or variational autoencoder. That was a result of some of the computer science research that we found and researched. So what makes a model, well, how can you tell if a model you've chosen is working? How can you tell that like you're improving your project? And one way I think that's most common is the improving just like human eye level resemblance of the original data. So can we say with certainty that like it's a better result if we replicate the original training data set? And on the left is a lower resolution image of the DC GAN training, and on the right is a style GAN training on 512 resolution. And while I do see values in this way of thinking, so the closer it is to original data, the harder it is to discern the difference between the fake and the original, the better it must be. I think that's an intuitive thinking, and there is merit to that. And there are a lot of like researches going into improving resemblancy. However, I also want to consider another possibility. And that is what I'm thinking a lot in terms of explainable AI. So a lot of these like AI model neural networks, the challenge we're seeing is that like it's got such a black box nature. So you gather like some data, you throw it in, and then it'll start making results. But how exactly it is happening, how exactly the learning is happening within the model it largely remains as a black box process. So there has been a lot of thoughts going in the field to work towards explainable model. So a lot of the current process, or like I'm sure like as you've worked with like 2D and 2.5D data, that like you're not exactly like sure why certain things are happening when you train a model or when you use this like ML enabled process. So the step towards explainable AI is that we have a better understanding of why certain processes happen. So there's an explainable data part, and then explainable predictions. When you have a prediction, you know exactly why that's happening. And also explainable algorithms. So what part of the algorithm contributes to certain results versus does not. And thinking back into our data set, this was our attempt at navigable, explainable results. But with clear limitations that it does not explain why certain things are clustered in some ways. And I think this kind of mapping is a step towards that explainable and navigable results of these training. But I think there are still like more opportunities that we can explore and push forward. And that is by semantic embeddings. So meaning when there's a 3D shape, easy way to understand like and represent and abstract the shape is through certain characteristics of that shape. So for example, this is a medial axis of the knot surface I presented earlier. And there are many ways to describe these shapes with like shape metrics. So this is a shape distribution of like different 3D shapes represented as a histogram or with some of the shape similarity metrics. So you're comparing like one 3D shape to another. And this kind of research is actually borrowed a lot from like protein shape research. So we looked at some of these results and like see how they are representing different kinds of protein shapes in this high dimensional space. So just revisiting this process, I think these analytical embeddings of like, okay, this is a shape, but then this is how we are evaluating this shape, and this is a metric by which we are analyzing this data point. I think that level of semantic overlay is useful and will work towards this explainable AI ML process. And hopefully that'll lead us to a point where we can fine-tune these kinds of metrics for a specific 3D shape and be able to train specifically based on like subset of these that meet certain analytical criteria. And this is a project by and Professor Andrew Witt and his partner Tobias Nolte at Certain Measured. So I worked with him at Harvard GSD, and this is a project in which we're scanning the 2D shapes footprints and trying to make sense of like what their like topological characteristics are. So these kinds of feature embedding or semantic embedding of each data point will help us push towards a neural net process machine learning project that makes more sense and where we can control better of these results. Last point I want to make about these like learnings and opportunities in the 3D shape representation learning space in architecture and design in general is accelerating the loop, iterative loop, inactive loop in design. One big need I see is large depository of 3D data is currently lacking, and how we're processing because of the challenges I posed and described, you know, in relation to data collection, generation, and processing. There isn't a streamlined, like standard way to access large depository of data. And actually that goes similarly with 2D data as well. We have a very limited like sets of data sets that most like researchers work with. So that's why we keep seeing the same celebrity faces or the handwritten digit data sets that are being used in the ML AI research space. And I think that lack is even more severe in 3D data space, and particularly as it relates to built environment. So this is a collective need we should address to push our discipline forward towards a data-driven design process and design science. And another need I observe is the need for making sense of the social data. So I work at Spatio Metrics and working towards making sense of these like plan data in social terms. And we can really conceive and imagine a potential of a different future where data-driven workflows and design extend beyond BIM models and the components that make up a building, but rather towards a true social and spatio-social data science process where we're really capturing large-scale data sets that consist of qualitative spatial characteristics and data about the social health and operational outcomes that occur within the architecture. So if there's a floor plan, let's say this is a healthcare building, like a hospital, then how do we evaluate like the performance of this plan up against another ones? And how do we capture how people are actually using this building? And how can we improve the design based on these data sets? And this is another company I worked at, Spacemaker, and they were working towards a similar goal of making design option more explainable with these like different kinds of metrics, not only just the traditional like square footage data, but what kind of environmental qualities do you get? Like how much daylight do you get, sunlight do you get, wind load, and by making these data analysis explicit with each of the design option, we're able to move towards a more rigorous process of evaluating design options and arriving at a design proposal as a discipline. So these are some thoughts that we can keep discussing as a discipline and a field to push us forward as a discipline. So as a conclusive remark towards design science, we've seen this like explosion of data and data storage and being able to compute and process this data with computing power. And what does that leave us as designers and architectural design professional? So we know like how machine learning works. There's a design, there's a data, and then there's a question you want to answer, and you train with like some algorithms, whether that's GAN or some other kind of networks. And then we make sense of this data, and we also make prediction. But how can we go from a component-based approach in conceiving data of buildings that's about components, pipes, building elements of this building information management, to really capturing social data and how the built environment is really structured? I think that's the question I want to leave with you guys. And I think this level of like social cultural dimension of data is where us designers are working within. Mainly the aesthetics of it, or cultural implications, or real social implications of a space. And I hope the sequence of this workshop, going from 2D to 2.5D to 3D today, will help you conceive your project maybe within these dimensions of data, model, and your project. And so that is it. And I'd like to open up to questions and discussions about any part of the discussion today. Thank you.
Thank you, Gia. It's like very interesting to see your diverse project and researches. And then I think it's very well align with our the topic ranging from the 2D and 2.5D and to eventually like 3D. Yeah. So anyone like just have question, just unmute yourself or write down your question in our the chatting box. So before just getting the question from the participant, I would like to ask you like based on your this the long the experiences, is the architecture machine possible, do you think? And if possible, what's your definition for an architecture machine that could possible pass the Turing test?
I muted.
Yeah.
That's a really interesting question, and I think something I guess like anyone who's like fascinated in the fields of like computational design probably grapple with, like, can a machine really be an architectural designer? Can a machine be an urban designer? I think these are like questions we have back of our mind and some hopeful thoughts we have as we're working with these kind of tools, right? I don't know, at least like I share that sentiment. So possibility wise, it is possible, but probability of like happening within certain time scope is, I think, a different matter. Because mainly for like, yeah, like probably two or three reasons. Like first, has to do with the architecture as a discipline and design as a complex problem space, meaning we're not trying to like optimize for like a set of hard constraints, but there are so many soft constraints at task and at hand that there isn't a clear path forward to optimize for that. I mean, we can make a building, but could that really resemble a design done by a skilled designer? I think that's a two separate questions. I think yes, like even with like current deterministic processes, so like we can have machines like spit out building options, right? But can we get at like quality design? Can we get at a machine that can design as a skilled and a good designer would be a different question. And I think that has to do with the ability for us to get at general artificial intelligence, which we haven't seen yet. But when it's I think like a strategy problem, like playing Go or playing chess, there are a set of rules that we can impose, and we've seen that succeed with AlphaGo and other kind of strategy playing game machines. And if we gamify architectural design process in that way, it could be possible and probable within like an immediate scope. But I think the separate question would be like, would that suffice? Would that really fulfill the discipline of design and architectural practice and its value within humanity, which is like to make new aesthetics or come up with new kind of human expression? I think that's a different kind of questions we're grappling with. So that's one part of my answer. And I think second point is has to do with the points I made in the lecture portion earlier. So the data availability is big. I think there are easier data to capture, which is more objective and hard constrained. Have you visited this space? Have you visited this grocery store at this hour? I think these are kinds of human activities that are easier to capture with the proliferation of like personal devices and ways we can capture these data through a lot of the platforms. And this is being done, right? So we know like how this is happening. But different kinds of questions is, do we have an accurate representation of buildings in the world? Or do we have accurate representation of like how people use the space? And I'd say like data availability and data capture there is below like 1% of like how people are actually using the built environments and how built environments are actually constructed. Because it's not just the street view of facades, it's not just the volumetric distribution of like where buildings are from point cloud lidar scan, but it is also about how people are feeling in this space. And that feel is hard to capture with these kinds of like objective data collection methods. And that is going to require us to really rethink and discuss as a field or as a society in terms of like, how do we want to evaluate a good space? How do we want to evaluate a space that works better for certain people or for larger pockets of like population in terms of people's well-being? Or do we want to value productivity? Do we want to value efficiency, or do we want to value like other soft aspects of building and space and human activities therein that are not specifically captured in like hard terms? So this becomes a value question then, which leads to my third point. So we might imagine a future where we can like capture all this data, have these data available and process at scale. But if we want to make that value decision about, okay, what's a good building design, what's a good architecture, I think that's gonna be the harder challenge to arrive at one singular architectural machine that does all these tasks, because it's really about the soft constraints of these rather humanistic process of design, which is proving to be harder to be replaced by machines currently. And I think that poses like bigger questions of ethics and values and how we as society almost like value aesthetics and cultural expressions. So yeah, that would be my 3 points on your question.
Yeah, it's like quite great answer. Yeah.
If you don't mind, I would like also to.
Yeah, please jump
there's
on.
Someone. Okay, there's someone who raised his hand, so maybe he can ask, and then I would ask later. So, or it was a clapping. Okay. Okay. So first of all, thanks a lot for the amazing presentation. And yeah, actually, I would also take from your last words and last, let's say, prediction of what could happen in the future regarding this aspect, to ask you in a certain personal opinion. For example, if we have, let's say, the basic concept of garbage in equal garbage out. So for instance, if you take if you have the latent space or if you have an input of data, which not necessarily 100% correct or 100% perfect, which is mostly the case in design, because in design also with respect to aesthetics, as you have mentioned, and with respect to people's opinion. Mm-hmm. So definitely there is no 100% a certain building that everybody agrees that it's a perfect building. So, I mean, even for us, we are not producing perfect buildings. So I think at some point also we can give the stage for the machine to try. So I don't know, maybe that could happen. So in this way of conversation, I was wondering, the way of 3D GAN, or the way of this kind of machine learning is based on entering data as an input with respect to another kind of machine intelligence, like reinforcement learning, like AlphaStar or AlphaGo, where you have an infinite, or depending on the state space that you're having to play with. So how, in your opinion, how we could reach the balance of trying to reduce to find an considerable amount of data that could support taking decisions, and at the same time reaching addressing the problem of architecture where we have a high degree of state space that we can somehow try to reduce and make, let's say, a scenario based on reinforcement learning. So this is the first question. And the second is regarding your presentation, regarding the topology, which I did not understand quite well, because in the topology, there was something like a graph-based system, which I didn't understand how it was translated into histogram. So if it's graph-based, so we have nodes and vertices, and then it's transferred to histogram, or there was another way? Thank you.
Oh, yeah. So I'll just answer the easy one first. So I'm constantly evaluating like how to compare and evaluate a 3D shape, right? Like it's not a pure, I mean, I think that same question could be asked in 2D images too, because like, I think like easier question is like, what is this picture of? And we do see like machines like getting quite good at that. Like this is a person, this is that. But I think coming up with like metrics that capture the complexity of like a shape or an image is a harder question. Like it's one thing to describe and it's another thing to evaluate. So first, I think at the descriptive level, like tools like topology can be useful. And the histogram is an example to show the similarity metrics of 3D shapes. So you have like, so it's a O of n square kind of complexity. So you have like, I don't know, n number of shapes, then you compare everything to everything else. So you're permuting that. And then you're getting at that similarity of like, okay, am I similar to this shape, to that shape, which is kind of like, I think, a resemblance of like our human process of design, which is based on precedence and typology. So there is this like level of, I think, like comparison and relative scales that are embedded in like our architectural design process. So that's that like small tiny fraction of attempt at evaluation of a shape. So yes, I think like the skeleton description of a shape is more descriptive, but that doesn't tell us much about like performative or evaluative aspect of that like specific data point, whether that's a 2D image or a 3D shape. So I think like a more interesting and helpful question to ask is, okay, we have this shape, we have this image, or we have this building, we have this architectural design that consists of like certain spatial configurations, but also shapes and aesthetics and cultural expressions, and also certain like performative results that impact built environment, cities, and people in like XYZ way. Then how can we evaluate that? And how can we compare that option up against everything else? And how can we arrive at like, I don't know, not even like one singular optimal like design, but like maybe like handful of them. So I think that's like a tiny fraction of like step towards being able to understand and scope the space of design problem and be able to put that into a communicable way. And you know, I think there's like a famous quote about like you only know what you can like put into words or something like that. So it is in that ethos of trying to be able to describe a building design or architecture in a communicable, consistent, reliable way, so we can create this collective intelligence about a built environment. So I think that leads like nicely into your first part of the question, which is slipping me a little bit. Like, could you remind me of the first part of the question?
Yeah, I was just asking like to what extent like we have more or less two parts of machine learning, or two I forgot the word. Um, um, Two types of machine learning. One which is based on the input that a human is providing, like supervised learning, and then we have and there is also unsupervised, but there is, on the other hand, there is reinforcement learning, where you have an infinite space depending on the state space that you're having. So you pick you try to minimize this state space to create sort of scenario like what we have seen in AlphaStar, AlphaGo. So in your opinion, how we can address the problem of architecture, trying to get like some more or less the benefits of both ways at the same time?
Yeah, it's a really good question. I think first part, I think it wouldn't be too hard to actually arrive at a building design or like handful of options that can perform well, whether that's energetically or efficiency wise. I think we can probably do it within like a reasonable time frame. I think like second part of like what you're proposing in terms of like scenario testing, like what if this building is like this height and like what's the impact in the built environment? I think that's like harder. And I'd like to make an analogy to like maybe like trying to make a movie machine. Like, yes, it can make like certain like sequence of images for like 90 minutes to play, but can that make like some sense? I like in terms of like literature or in terms of like plot line and emotional like value it's invoking to us. And those are, I think, like harder questions to answer. And maybe if we like compare it to like that level of culture production, like such as film, then I think we can like maybe have a clue about like, okay, like how can we like improve like XYZ aspects of like these generations, or how can we understand uh, emotional or like well-being aspect of a building design on like humans. Yeah, so that's I think that's still a question to be explored. But on your point about, I think, like garbage in, garbage out, I think that's very accurate. So just whatever project you do today or in the future with machine learning, just take it with a grain of salt. And like, I think everything is like experimental at this point. And, you know, yeah, and that question about, I think like, okay, like I have this like whole set of data set that I fed into the neural net, and then I get like some results. Then I think like it's our job to constantly ask, okay, like why did this happen? Like what kind of data led to this? What other model, like part of the pipeline, can I improve? And so I did this like data and like model part, like so what? So I think like asking that like question about like so what will actually help you enhance your process and thoughts towards this this new phenomena and methods in a constructive way.
Thank you.
Okay. And any other questions, you guys?
Yeah, I have a question.
Yeah.
Hi, Gia. Thank you for this very interesting presentation. I actually found very well interesting how your work fluctuates between and seems to retrofit between practice and discipline. And I particularly found interesting in the latter work that was presented, the possibility to move away from the paradigm of the human eye resemblancy, through the mapping of the latent information or the semantic embeddings that you showed, and use them as a device to come up with new aesthetics. But apart from that very impressive project that you showed from Manhattan, that actually was, to me, seemed like very auspiciously related to the Manhattan transcripts. How do you see, to what level do you see that these tools can be used in the professional field, just like the social media metrics companies that you said that you worked at, or Spacemaker? What challenges do you find to push this kind of aesthetic out there, and not just having the more standard simple blocks arrangements?
It's a really good question, and I think one way, and like one I think potential we're all excited about, probably, I'm just projecting my wish there, is that by being able to show what a good design can achieve in concrete terms, can convince other people to be design advocates. So if you show that, like, okay, you will spend a little more in terms of cost here, but your building occupants will have XYZ effects by your design because of it has more sunlight, it has more daylight, and that increases like well-being of your occupants. It can lead to your like long-term value. So I think that's a really useful tool to lead conversations with stakeholders who are not trained in design, or whose primary function is not design. So I think that's one concrete example. And I think second part, like aesthetics is hard because there isn't an evaluative criteria that we can say that like, oh, this is better aesthetics than that. So there isn't a, so that's, I think, a part that I see as like the biggest gap between descriptive criteria and evaluative criteria. And there's a dimension of like being a little early to be a good designer aesthetically, so that you cannot really like retroactively apply your current criteria to evaluate something that would be like, like forward or pioneering in terms of like cultural or artistic expressions, right? So I think that's a question to be considered like collectively. And I think like it's the same reason it's like hard to make like an AI art that is not just like some like distorted like faces. So and I think there was like a third part I wanted to answer to that. Like, how does this help? Yeah, I forgot the third point, but yeah.
Yeah, thank you. I just thought it was really fascinating how you actually achieved some very realistic elevations in that project in New York that you showed, as opposed to as the result that you normally find in the Spacemaker, which is, it's great as a tool for arrangements, but it doesn't really quite gives you like a final product, or closer to, doesn't get you closer to a final product, right?
Yeah. I mean, that's a really good question. I think like I can answer that actually in two ways. Like first is there's a lot of, I think, like human curation going into like working with this like human machine process. So there's like even if you feed the machine, like you'll have to like cherry pick like what the good results are. And I think that's like where the new agency of a designer is in this like age of machine intelligence. And secondly, I think even in the professional practice or industry, even if like, people are excited about potential, it takes time to actually have this part of the design process and design conversation. So people know like, okay, like machines can compute like views like way better, but like we have our process, and like it's hard to change that process, whether it's a design firm or a city planning process or a development process. So I think that's another like question, like in the more practical, like professional side. So we have these tools at hand. How do we adopt it in the current process is, I think, another big hurdle that I didn't discuss, but would be really useful, that can have like immediate impact in our current design profession.
Sure, thank you. Yeah.
Okay, so it's time to wrap up in the first session. So thanks, Dia, for coming today and sharing your like very exciting your project and researches. And then Gia will also join in the final the presentation. So see you later then. And then we are gonna switch our gear to the more the practical one. So yeah. So thanks again, Gia, coming today. And then yeah, see you then later.
Okay,
Thank you,
thanks so
Gia.
much for having me. And I hope you guys have fun with the tools and think about these issues as we go forward. And I can't wait to see the final results on Friday.
Thank you.
Thank you.
Okay,
Thanks so much.
bye.
Alrighty. Yeah, I guess yeah, after like such a wonderful lecture on like the application of 3D GANs, we're gonna really dive deep into how the 3D GANs are actually implemented and how you can use like the existing toolkits to curate like a 3D GAN experiment that you can customize. So I think yeah, let me just share my screen and start the presentation. Yeah, so today I think we're gonna go through like the more hands-on parts of how we can do the neural 3D modeling with the 3D GANs. So yeah, I think today's like just a general schedule of what's gonna happen. So first of all, we're gonna start the training of your 3D GAN objects in the Google Colab, because it's gonna take quite some time for you to get the results. So if we start the trainings at the beginning of the class and like use a small epoch number, then we are likely to get a result like probably by the end of the class today. And when you start the training in the Colab, we're gonna proceed with the just the mini presentations and introduction to image convolutions, where you're gonna be using Colab and the actual research medias that are the machine learning research community are using, which are the modern deep learning libraries PyTorch. And we're going to use explore how PyTorch can perform the 2D convolutions as well as like creating a very vanilla neural networks for get a feeling of how this thing actually works. And after the convolution part, we're going to take a small break and take a look at how your training goes in your Colab. And after the break, we're going to introduce like some visualizations about how you can use Grasshopper to integrate what we're doing today with what we have yesterday, and for the 2D and 2.5D part to animate your 3D GAN latent-based work together with your texture 2D GAN latent-based work. So in this part, we're gonna introduce some concepts of the computer graphics pipeline that are used as an industry standards, as well as like the introduction to how shaders works in Grasshopper with the latest feature of Rhino called GHGL. But this feature requires that you have a Windows machine and a Rhino 7 installed on a computer. So if you do not have Rhino 7, this will not work. So please make sure that you have Rhino 7 version on your computer in order to run all the scripts that we are gonna go through today. And the last part of today's workshop will be like integrating everything together, including the generated models from the 3D GAN, as well as the GHGL shaders that we're gonna play with. And if we still have some time after the animation part, we're gonna go through some like probably like a reading list of the state-of-the-art neural procedural modeling research in the domain in the computer graphics today. And yeah, that's all of today's schedule. So first of all, I would like to invite everyone to get hands-on about the 3D GAN training process. I know some of you have been requesting the access to the documents because you're not using the exact same email for your Google Colab for registering the workshops. So yeah, I'm just doing that by hand. So please let me know if you can still not access any of the 3D GAN's Jupyter Notebook. So yeah, can you let me know, give me a thumbs up if you, or just like jump in if you cannot access the Colab notebook. All right, I'm adding some of you into the Google Colab because you do not yet have a correct email. Wait a second. All right. Okay. I think I've added you manually in this hand to the Colab. Okay. Now let's keep going with how you can actually upload your data set and get the training going. So, yep. So is everyone able to run the results already? Oops. Let me paste the link to the notebook as well. Is everyone with me on this page? Like the get the 3D GAN working. Okay. Yeah. So if you're done with this, then we're gonna go through how you actually configure your 3D GANs in the Colab. So before we actually run the notebook, I would like to suggest that you upload your data set, to your Google Drive address. Okay, so now we're gonna open the Colab address, and for me, I upload as the same as we did before. Just put all of my files in the same folder of DF 2021, and yeah, just make sure you have you keep track of which is the dataset directory that you have in your Google Colab in your Google Drive. And then we're going to run the first cell in the Colab. It's nothing special, but installing all the required libraries and import some of the dependencies that we're going to be using for running the 3D GANs. So mainly it's going to be using the PyTorch library for doing deep learning. And one thing you have to make sure, you have to make sure before you run the Colab is that you have to make sure that your runtime is in the GPU so that you can have the CUDA acceleration to run deep learning on the graphics card, which can greatly accelerate your training process. So you can access that in the runtime, change runtime type, and hardware accelerator, GPU. That's it. And once you make sure you have the GPU running, you just run through the first cell to install everything. If you don't like it, you can just clear the output for this one. And then you're gonna mount your Google Drive to your to the current working directory of your Jupyter Notebook. Once you mount your drive, you're gonna see that in the content drive, my drive, and DF 2021, and that's it. So then we can import all the libraries from the Google Colab and all the dependencies that we're going to be using for the training. And here you can also import the libraries that we are using for the visualization, and run this cell after the image plotting for the sanity check to see whether CUDA is available. If it's false, then that means that you're not using GPU but using CPU instead. So in that sense, just change the runtime step of your files, and then that's it. Okay, now since we have made sure that you have your Colab running on the GPU acceleration, then what we're gonna do is that we're gonna do some like dataset inspections, or like we call it EDA in the data science domain, to just keep track of what type of data that you're working with. So I stored my data in the file directory plus we're gonna use the chair dataset for today because it has like a better performance. So what we're gonna do is that we're gonna remember the file name and replace that with the chair, and probably chairs 0002 in box. Sorry, it's wrong. Missed the slash. So now if you have the directory in the correct format, then you're gonna use the util functions to plot your voxels that you get from the binvox. It's gonna take a while to run this cell actually, so we're gonna wait for that. Okay, now we have it. Oops. So now you can see that this is the chair that we use. One of the chairs that we use for training is actually quite Mondrian, I feel like. And it's in a 64 by 64 by 64 definition for the voxelization process. And so that means that we're in a good shape, and this is like in the correct scale. And then we're gonna run the actual training. We're gonna use the training using this command line prompting in Google Colab, so that you don't need to run any local computing resources, because it's quite heavy actually. It requires like a large memory area of your GPU to be able to run this thread again. But one thing that you have to be careful is that you have to make sure that your output directory is like a subfolder of your content drive and my drive. Otherwise, Google will just clear your data if you do not, if your runtime expires. So just make sure you have everything correct, especially the data directory and the output directory, just customized to your own Google Drive. And we can also fine tune some of the parameters. So I would suggest to use an epochs of 200 just to get the first taste of how that feels and have a small batch size of say 16. We can use 16 for this because we have a lot of data here for the chair dataset. But if you have a small dataset set, I would encourage you to use like a small batch set so that you have more gradient update steps. So the default you can use 8, and that is I think better, just to run it multiple times updates through the dataset, and then you run the cell. Then if everything runs correctly, you should be able to see the printing of the hyperparameters. And once you see this line, once you see this line running, it means that you are in the correct training mode. We're gonna wait until the first episode ends, and we're gonna stop the screen sharing, and we're gonna have a troubleshooting session for anyone who doesn't run this, because we're gonna get this Jupyter Notebook running throughout the process of today's workshop, and we're gonna come back again to see when your Jupyter Notebooks finish the training process. Okay, so now it has the image saved commands printed. It means that the first second episodes are finished training. So just to get it running in the back, and you're gonna see the logo turns gray. just check your notebook like every 20 minutes. So when it turns again into the yellow color, it means that you can run the just the Jupyter notebook. Sorry, you mean that the training is finished and you're in good shape to just run it just to inspect your results. So since my output directory is actually the DF 2021 output, so you're gonna save the results here, depending on which model name you just put in. So this is just using one of the shared training method examples. Once you open it, you're gonna have images, logs, which is the inspection for a TensorFlow, and models, which saves all the checkpoints, actually, the checkpoints of your PyTorch. So it actually should be something like, something like this, the discriminator, checkpoints, epochs, numbers, PTH, and most importantly, we have the generator epochs, PTH. And the images are actually the intermediate training results of your data set. So I think this is the one that was trained on one of the architecture data set. And as you can see here, it's the convergence of the 3D GAN is actually just a quite tricky problem. Because I didn't have such a clean data set on the one that I'm using, it didn't converge to an optimal result. So what type of data that you're using for the 3D GAN training is really tricky. And you have to make sure that you're using the correct format of objects for the training. All right. Once you see your image models in your test and the model in your model name and test subdirectory, it means that you're on the correct track. So I'm gonna stop my screen sharing, and you're gonna have a a really quick 7-minute break until 11. And I'll use this time as a debugging session. So if anyone has any trouble opening the 3D GAN training Jupyter notebook, just let me know. Yeah.
Ronja, I have one question.
Yeah.
So what we need in Google Drive is only the Beambox files, right? Or
yeah, exactly. You only need the Beambox. Yeah.
Okay. Okay.
So does anyone have any trouble running the cells? You can use my sample file if you do not yet have the 3D data.
I have a problem with the setup file directory command on Colab. If that makes sense.
Just go ahead. You can share a screen if you want.
Okay, sure.
Okay.
Can you see my screen?
Yes.
Yep. Okay, so I have previously tried to run this cell, and when I refreshed the page and tried it again, it gave me a warning, but
it's okay.
think that's not.
So
okay.
Yeah.
And the next step is always giving me errors. So.
You have to change the name actually. So just screw up the file directory. If you do not put it under DF 2021, then that's going to be a different name.
No, I did. I created a folder. Yeah, with the same name, but.
Wait a second.
Should I go?
Oh, I see. Really sorry about that. I see what your problem is. I think there's one step that I missed in the process that, you have to copy and paste the latest file to your your Dropbox. Sorry, to your Google Drive. Let me just reshare my screen and
Okay, sorry.
how that is done. Users for. All right, sorry about this. I actually missed one of the steps that you have to do to set up the 3D GAN training. So please everyone just download this folder called SRC, the source folder, and put that into the training directory of whichever your folder is. So yeah, the way that you do that is you just upload the source directly into the DF 2021 folder, or whichever you just organize all your files, and then you should be in good shape. Yeah, really sorry about this. I just used my configurations for so long and didn't realize that you don't yet still have access to these files.
Okay, and you said something about something deleting all of the drive files. What was that? If I got that correctly, or?
Yeah, it's just like wait a minute. So it's actually here. Just replace the file directory with replace the DF 2021 with whichever you are working on, like whichever folder you are working with. Yeah.
Okay. I get it. Thank you so much.
Yeah, no worries. And you can also alternatively find the file inside this Day3 toolkit of the subfolder of toolkit. And right, does anyone have any other questions or troubles running the setup? Okay, if not, we're gonna take like a really short like 3-minute break and just come back again. Sorry, Carlos, do you have any?
I don't know if you can just open your Google Drive and to see what folders do we need to have there.
Oh yeah, sure, definitely. Yeah, sorry about the confusion, but yeah, so the only folder that you have to make sure that you have is the SRC, the source code folder. So inside the source code, you have all those like Python files that you can be using for as the library that I just wrote for the workshop, and part of them are also from another GitHub directory about 3D GAN. And once you have the source folder, it's always like a good habit to separate your input, your training data, like just you put them in whichever folder, and your output data. Just make sure that you do not, just pollute all the folder structure, all the folder structure. So once you have your source, your input and output, you're good to go. Just replace the file directory on this line with whichever is the parent folder of all your files, and then just make sure that your data directory is the input folder, and the output directory is points to the output folder in your Google Drive, and then you're in English.
Okay, thanks.
Excuse me, what was the source folder for, and what were inside these files? Where can I get them?
I just uploaded into the Discord channel, just so you know, announcement.
Okay.
Yeah, just you can download that and unzip it and upload into your parent directory of all these files. Yeah.
Could you just show your setup file directory once more?
Oh yeah, this one.
On Colab.
Yeah. This one?
Yeah, the last line out there, which file do we have to refer to there? Yeah, out where your cursor is.
Oh, this one points to your personal, there's a universal folder inside of, your Google Drive, and that points to the Colab notebooks. It's actually not necessary. So, and I believe that it will always be there. If you, oh, sorry, it's actually be like this. Yeah, just remove the space between my drive and this one is actually, you do not need to customize it because it will be custom. It will be copied whichever your Google Drive looks like. Yeah, it always have the Colab notebooks folder. So, but the only one that you have to care about is the file directory. Yeah.
All right, thank you.
Yeah, no worries.
One more question, please. The file directory is the main file, the main folder in which you have all the source data, but the data is inside another folder. In this is in another subfolder, right?
Yeah. Yeah. Your data folder does not have to be in the same directory as even, but it's always like a good habit just to maintain your source file like a data and output in 3 different folders, so that you do not put your data folder inside the source or vice versa. Yeah. So these 2 does not have to be in this folder, but it's just for me to manage everything together. Yeah.
Yeah, I understand. But I mean, the file directory refers to the file in which, it refers to this folder, which is DF2021.
Yeah, that's right. It's the parent folder of the source. Yeah, it has to be the parent folder of the source. Yeah.
Okay. And where is the data itself? In which folder? So it's independent of the source. Okay. Okay.
Depending on which type of, you can name it whichever way you like. I just named it Renjatian 3D and just put them in categories like this. And you can, yeah.
Yeah,
but just make sure here,
maybe.
The data directory is the actual directory that you put your data inside. Yeah. And the output directory is where you want your output to be. Yeah.
On Colab, could you go to the plot images for sanity check area?
Yeah. Here. Yeah.
Yeah. Again, so the first link out there.
This one.
Yes. So that is your subfolder you have to put, right?
Yeah. Oh, yeah. That's right. Yeah. So that's actually pointing to one of the Beamworks file that you have in your, system.
So when I play, I get something as a Stack Overflow thing.
For this?
Yes.
Did you run this CUDA available?
I think so. No, I might not have. Okay, one sec. I'll just.
If you're not, you just may not be running on a GPU device then. Yeah.
Oh.
Just make sure you are running with the GPU. Otherwise, the CPU is not enough for this Colab.
Yes, I am on GPU.
So you click on runtime, change runtime type, and GPU. And do you have like access to changing the runtime shape?
Oh no, I don't have that.
No worries. So this should be fine. But you have your GPU acceleration, but your overflow. Can you just share your screen? How large is your Beamworks file?
One sec. I'll just have to join from my other laptop. Give me 2 minutes.
Okay.
Let me ask a question.
Yeah,
Maybe I can just share the screen.
Yeah.
So here, there's like a name arrow, like the Beambox, like RW, but it's not defined.
Did you run the import file, the import cell, just above the plot image percentage check? You did not run it, right?
Which one?
So let me just put an annotation. Oops. It's this one. You have to run this.
Oh, this one?
No, just the import one you didn't run. This one you didn't run. Yeah.
Okay.
Oh yeah. If you get it, if you get that cell correct, then you mean that you are in good shape. Yeah. Then you can run the next cell. If your binwalk is too large, like 2 gigabytes, that will be probably like crash. But I don't think that will likely to happen.
Yeah, hi, I'll just share my screen.
Okay.
So I'm having the same, and I have played this earlier.
It's actually is directory arrow. So where did you put your data?
So my data is in this file.
Okay.
And within that, this has all the.
You have to add another slash after your binwalk. Yeah.
Oh, yeah, yeah.
Can I try to run that again? Can you open your binwalk folder?
It's 7142.
Yeah, just whichever binwalks you just you have to copy the name of the file actually. So yeah, for example, this one just
last name is Chen, CHEN. Date of birth is January 24th, 1995.
Probably like a shorter one with a shorter name.
Right.
You have to paste your binwalks file name actually after the binwalks folder.
So out here, you mean?
Yeah, whichever file you wanna visualize, just you have to put the file names after it. Yeah.
Oh. All right.
Yeah, just that's it. Just
This.
Yep.
But I thought we had to input all of our binworks files, like all of them for the process. This way, I'll only be one.
No, this is only visualizing one. Yeah, just for sanity check, just make sure that you are not, you are not doing things correctly. You miss a quotation mark after your binwalks.
Out here.
Before comma.
Oh,
yeah,
sorry.
before the comma. Yeah.
I'm new to this.
Okay, just run that again. Oh yeah, now you see there should be able to plot it. But it seems that you're still running on your CPU.
Oh no, it wasn't.
It's runtime. It's runtime. Sorry, it's not novel. It's runtime. Change runtime setting. Okay, now you got it.
All right. This is fine, right?
Sorry.
This is fine, right? This worked.
Yeah, this is fine. It means that your voxel is. But it seems that the direction is not correct. So, yeah. It might be upside down.
Yeah, I think it's rotated 90 degrees along the x-axis. I'll check the original file. All right, thank you.
Yeah, no worries. Or does anyone still do not have access to the notebook? Just go ahead, Faye. Yeah.
Yeah, like I also feel might be like my model was showing an upside down, like basically upside down position. Are there like any reason you can think of like why it's happening?
Wait, all of your files are upside down?
I just test like one of them, but it seems like an upside down position. But anyway, I can test others.
Yeah, it's probably one of the reasons is that you're running your when you do the OBJ exporting, you might select exporting Z as exporting Y as OBJ Z in your Rhino setting. So that might be a problem. Any issues?
Another question, sorry.
Yeah, go ahead. Yeah.
I'm just wondering what's this line about? Like, what's the data directory here? Like,
this points to the folder where you put your Beambox files. Yeah.
Oh, okay. So the stereo unify is actually the Beambox file. Okay.
Yeah, exactly. Yeah, that's correct.
Ranja, can I share my screen for a second?
Yeah, go ahead. No worries.
I'm not seeing here my drive. Do you know why in this area?
Did you mount your Google Drive?
That's
no. It seems that if you run your cell, you have to start from the beginning. Sorry.
So how do you mount it? I think I mounted it.
No, it seems that you start the runtime again sometime at some point. So if your cell does not have the number in front of it, it means that you have not running anything. So let me just annotate. So yeah, if you have a number here, that means that you run the cell. But if you do not, it means that you haven't. Maybe your machine just crashes, restarted in the server.
So should I just run it?
Yeah, just run everything from the beginning. Yeah.
Okay.
Yeah, so like that's the sanity check is just for make sure that your data comes in the correct file format, because Beambox is not like a intuitive data structure, and yeah, so we have to like inspect that like by hand in this like setting. So, but if you have the correct Rhino files, then you should be all set. So I see Dogga raise your hand. So
yeah, yes, sorry. Yeah. Can I share my screen next? Yeah.
Yeah. Of course.
Next. Yeah. Okay. No, after you. Oh, sorry. No.
No, it's fine. It's fine.
Did you successfully mount your drive, Carlos?
So when it's mounted, how do I know that?
Did you run the mount file, the mount cell? There's a cell running, for your Google mounting process.
I think you can share your screen again because I was planning to ask after you. Sorry about that. Sorry.
So where do I see that, Ranja?
Next cell, in the scroll down. Yeah, it's just run them in order. It's a setup file directly. You run this cell again. Yeah.
So now I should run the setup?
Yeah, run the setup. Yeah. Yeah, you can see there's a link, and then you copy your like the authorization code, and you just mount it. Yeah. So but if you want to inspect that in your like let's say the temporary tree, you have to like right click in this sample data and refresh. Right click. Sorry, there's a 3-point refresh here. Oh no, sorry, refresh here. Then you see your drive.
Okay, right. Yeah. Okay. Oh, I see. Okay.
Yeah. Sorry, this is kind of confusing, but that's life for if you really want to do like a machine learning research. That's usually the thing that you have to run.
Mm-hmm. Okay, so now that it's mounted, I just have to change the directories, right?
Yeah, just customize your own directory. Replace the name of mine. Just use yours instead.
Okay, thank you. Okay.
Yeah, no worries. And yeah, then I think it's Doga.
Yeah, sure. So I have a problem again. It's with the same place, I have imported, you see the source file here, but it's not, I don't know what to say, it's not reading or something.
Yeah. Did you upload the source folder to your drive?
Yes, I did.
Okay.
This, right?
Okay. Yeah, nice.
Yeah.
What does it look like in your collab then?
Okay.
Can I scroll up?
Up. Okay, sorry.
Yes, scroll up and up and up. Interesting.
Should I try with a different Gmail address, or does that matter? I don't know.
Oh, is this the same Google Drive as your collab?
Mm-hmm.
If you're using the same Google account, you should be able to mount it. Can you just click into the left side of the? Yes. Oh yeah, just in the drive, in my drive, and
I have everything.
EF 2020. Okay, that's strange.
Yeah. So should I keep it open?
Wait a second. Let me see. You I think it's a /bug or /bug, and can you try to run the 24 again?
Yeah. Okay, then next, yeah?
Yeah, then the next.
Mm-hmm. Again.
That's really strange. No more names first. Can you go back into the source folder in your drive?
Mm-hmm.
Oh, we have the need. This never happens before in my side, and oh, wait a second. Can you double check what's the name of your Google the Colab notebook directory?
Mm-hmm.
Do you have something called Colab notebook in your folder? in your like the
Drive.
yeah, in your drive. Yeah, Mac because of the language.
Yeah.
Oh, the same Colab notebooks. Well, that's very strange. Okay.
But it's not in here, so.
Oh, you have to have your, yeah, you have to have it, you know, inside. So where do you put your, it means that you might not be using the same like Colab notebook. Can you just do the file, save a copy in the drive?
Yeah, sure.
Yeah, save a copy in the drive. And that should be fine then, yeah.
Okay, I will try it again then. Thank you so much.
Yeah, no worries.
Yeah, Ranja, can I bother you again with the directories? So is this where I have to put my folder here in file there?
Oh no, it's actually the DF 2021 folder. Yeah, it's actually the parent folder for your, you know, for your source file. Yeah.
Okay, so then where is that? I should change the directories.
Yeah, can I go to your drive? Just the 3D dataset.
This one.
Oh, that one just your DF 2021. You don't need to change it if that's the same name. Yeah.
So I don't need to change. So
if your parent folder is named DF 2021 as well, you don't need to change it. That's the same. Yeah.
Okay, so then I should just run the next one, which is plot images for sanity check.
Yeah, just run everything from the top to the bottom, all the way to the do not miss anything in between. Yeah.
Why do I get an error here?
You have to change the file with open file directory plus your file name things. Yeah. So it's file directory plus I think it's called Fei Carlos 3D dataset and Binbox and something. No, not this one. The number 5.
Number 5. What is number 5?
Yeah, you have to replace this with your Binbox file location.
Here, this line.
Yeah, this line. Yeah.
Okay. I see.
Whichever, like probably Fei Carlos 3D dataset.
Like this, or just
Fei Carlos 3D dataset.
Okay.
And then your Binbox /Binbox.
All right.
// sorry, it's not backward slash.
Okay.
And then your Binbox file name. Yeah.
Oh, one file. So I choose.
Whichever one you think makes sense.
Whichever one. Okay.
No, you did not import the Binbox correctly. So
what's the error here?
Did you import the Binbox folder? Sorry, did you import the Binbox RW library? If you scroll up.
I think so. It's here.
No, I mean in the Colab. Yeah.
Okay, where is that? Where should I do that?
You did not run the file after number 3. You should run everything from the top. After the cell after number 3. Yes. The next one.
Next one.
Yeah, just run this. Yeah, you did not run this. No, the one above.
The one
above the plot for the sanity check.
True. Okay, this one.
No, the one above, sorry. The one above the cloud sanity. Yeah, this one. You did not run the import from 3D GANs. Yeah.
Oh, I see, okay.
No, see, like now you can run the plot without any problems. Yeah.
Oh, okay.
Yeah.
Okay. Okay, thank you. Thank you very much.
Yeah, no worries. Alrighty. So I think we can just keep going. Since like yeah, this takes like some time. So the server get the training starting. So if you have no problem running the training, then you can probably get the results by the end of the class day. If you have your data in the incorrect direction, just make sure you run the command line prompt. And we're gonna fix the orientation thing after. Don't run your training with your wrong data because you have a limited core training time per month. So if you expire the free limit, you're gonna be charged by Google. Or it's not. It means that you cannot access it anymore. So do not start a wrong like an incorrect training, but yeah, just test whether you can run that cell, the one that above the inspect loss convergence with the one above the inspect loss convergence with TensorBoard. Yeah. So if you just have your data directory correct and your output directory correct, then you should be able to run this cell without any problems. But just if you get the results correctly, it means that you're in good shape for the setup. But do not run the incorrect data if you have your access flip error. We're gonna fix it later after the class today. Yeah, so as Donald said, you might enable the default reorient Z to Y if you're importing OBJ to Rhino. Yeah, just uncheck that option when you do the file batch conversion. Yeah.
Can I ask another quick question? Like my notebook says, this notebook is open with private outputs. Outputs will not be saved. You can disable this in notebook setting. What does that mean actually?
It means like you're not saving the outputs. Like, it's like, you know, when you run the cell, there is something that gets printed every time, right? For example, success like import or image plotting. That means that you will not save those like those lines every time. You will not save the outputs, the temporary cache of your printing. If you want to change that, just go to Edit Notebook Settings and uncheck Omit Code. Sorry, just uncheck the Omit Code output when saving this notebook. Then you should be able to save your printing result. All right. Okay, so yeah, just like I'll be staying after class today for just additional debugging sessions, so we can solve more issues by that time. So, but just make sure you can run your 3D GAN training without any problems. Yeah. All right. So now we go to the second part of today's today's workshop, which is the mini presentations. So yeah, we would like to ask like each team or per individual, like if you want to present your work with the class, just jump and start the screen sharing. Yep.
It'd be great to get everyone's cameras on if you guys are okay with that, and we can keep this quite informal. Just a informal sharing, of what you guys have been up to, and later on we'll talk about the next project. and we might popcorn it again. So maybe I'll start with the first popcorn. Since Doga, you're first on my screen, would you mind starting if that's okay?
Yeah, sure. The slides, right? The presentation. Yeah. So I have prepared my presentation yesterday, so I didn't know my teammate. So I will be presenting my own work for now.
Doga, you are paired with Jose. Jose
Yeah.
Zuluaga.
I believe he's here right now. I saw his name. Yeah. So I'm starting my presentation, if that's okay. So on day one, I have collected some photos of the 20th century modern architecture, and we learned about runway ML, and we tried model options. These are some results of those. I tested some on my own after the class, and there's a video. Then we changed the runway with almost 200 photos and 7,000 steps. It took 7 hours almost for me. Then I have created the video, and this is the result. Also, I have generated some images in the runway after training the runway, and these are some of the results of that generated images. And on day two, we have created frames for Rhino, Grasshopper, and latent walk videos. Sorry, latent walk models. Yeah. And these are our experiments with different scripts. And that's it for my presentation. Yeah.
Thank you, Doga.
I hope that
really
was what you needed. I'm not sure if I got that correctly. So yeah, thank you.
So you use the same images from day one and you put them into.
Yeah.
Great. Do you want to popcorn to the next person?
Oh, okay. I see Carlos on my screen, so if that's okay.
Okay, sure. I'll share my screen. I didn't have time to make a slide show, but can show what I did in day one, which is so the data set that I collected was a series of about 85 images from just some generative design geometries that I had archived, and I used the Colab script to augment them by rotating them, and at the end I got to a number of 534. Yeah, I produced this video here. This one, which some of you have seen, and I selected the images very quickly, but I thought it was interesting. It was an interesting result. Like, for example, there are parts in which I think, because some of the images have black and white backgrounds, and some of them have like gradients. They start to have like a sort of a fog in some of the images, and then the latent space varies from that fog to black or white, right? So I'll just play the video right now. Just this one. And this is 3 3,000 steps with about 500 images. And I got very different results. So I think I used about 10 images to make this 1 minute and a half video. Yeah, here you can see some of that fog that I was talking about. And yeah, I think it's an interesting latent walk. Yeah, I mean, I could have searched more. I mean, I only refreshed like 3 times to get the images for the walks. But yeah, I was curious. I'd be curious to just use different images to produce maybe more different results. Like in the end, you're gonna see that this part, for example, is very different from the other ones, and it produces something different. Right? Yeah, that's it. Thank you.
Yeah, it's really beautiful. Yeah. Just curious, like, how did you generate those shapes? Is this like using Grasshopper or other like scripts?
Oh yeah. So they are made in a series of exercises utilizing Grasshopper and Python. And yeah, actually that's it. It was only Grasshopper and Python with Rhino renderings. They were very simple. Yeah.
Okay, that's really nice. Like, because I think you are using like language for the shape generation. So you have like, on the one hand, you have like the grammar for those shapes. On the other hand, you have like the actual 3D objects, right? So yeah, we're gonna cover these topics in lectures later today about like probably like the procedural grammar about and language and shape in the last part. And yeah, I think that's really have a lot of potential to develop this like shape language multimodal synthesis using this workflow. Yes, great. Yeah, you have the popcorn for the next person then.
Oh, sure. Okay, maybe I'll ping Hamid.
Yes. Okay. So so basically, I did not quite understand what we should present. So from one side, okay, I can also present what I have done in the previous couple of days, but also I was thinking what could be presented as a final product. So I just got the idea like half an hour before the final somehow scratch of an idea before the start of this session. So maybe I can just share the couple of slides that I have done so far. Can I?
Yeah, definitely.
So yeah, my idea, or the thing that I was thinking about is when you were discussing the thing about latent walk. So the thing that got to my mind, what if using also what you were explaining yesterday, so transforming the workflow of getting the latent space, the 2D images, and then compiling them together, and then performing or having the 2.5D. So the idea is, what if there is the ability to extract some information out of this 2D images, forming the meshes eventually, but immersing ourselves in these kind of meshes. So let's say we follow the same workflow as of yesterday, and then we use some sort of let's say Unity or something, and then we follow a camera inside of this path. Let's say, sorry, like something like this that we have done yesterday, and then we have like some sort of camera that's moving inside, and the idea is to think how much abstraction we have reached from the latent space. So we have the original images and then we follow by the process of having these hallucinations and then forming the meshes out of these hallucinations, and eventually forming this some sort of path. So my idea for a final project would be experiencing different paths for different people or for different latent spaces that were experimented in these sessions, and trying to immerse ourselves inside. So we get inside of this path and see what we could see, and compare this level of abstraction with the level of detail that we have in our original images. That's all. And for the idea of the latent walk, of course, the Gothic pictures were also done earlier before, also with Rafik Anadol and many other people, but I was curious to see this by myself. So I was just collecting around 550 or 600 images, and yeah, I tried to focus on special features of the Gothic architecture, and try to see how, yeah, and try to play with these images and see this kind of nightmare that we are seeing now. So it was pretty interesting. Yeah, that's all. Thank you.
Thanks a lot, Ahmed. This immersive idea is definitely really interesting. Look forward to seeing how it develops.
But one question, yeah, I don't know who is still with me also on the group, so I checked.
I can tell you right now.
Yeah.
Let's see. It's in the survey. So you are with Reza. Is Reza here in the call? Reza, let's see. Because we can give you the possibility to join a group of 2 and form 3. But we can talk about this maybe after. You want to ping pong it one more time?
Okay, I would ping pong to Arya Gupta.
Yeah, hi. Again, I haven't really prepared a presentation, but give me a moment, I'll just share my screen. Is it visible?
Yep.
All right. So I started with the idea of cityscapes, specifically paintings of cityscapes. So this data set was also available. A data set of a lot of paintings were available. So I kind of sorted through those data sets and I found this. So I used around 4,000 items and created a latent walk of art through cityscapes, of how cityscapes are perceived through art. And I found that pretty interesting. Now, actually, this is a 2.5 minute thing. So yeah, kind of adding on to the idea of how immersive it was, how Ahmed spoke. It's these kind of experiences that make this kind of immersiveness come in. Either way, so after this, I took the first 30 frames of my latent walk and I tried experimenting on Rhino through the scripts. So what I wanted to do out here is create a very different blurry version through the meshes that we were creating. So I kind of edited the script and added extra, like 4 supplementary scripts working together to create a very pixelated kind of version. It's a work in progress. Like I haven't really done it, but then this becomes like its own latent walk through a very particular chosen set of colors. So I'm just working on this, and yeah.
Great. Thanks so much, Ira. Looks great.
Thank you. I'll ping pong it to Nileen.
Yeah, sure. Hi everyone. So even I haven't made slides as such, but I can just go on with my progress so far. Okay, let me share my screen quickly. Am I audible, George?
Yeah, we can hear you. Great.
Okay, awesome. Yeah, awesome. So on the first day, like initially, I thought of having a data set of all the temples in India, and I was really interested in the way the latent work turns out, and I was sure of the idea that the intricacy temples have in India would be a good like a good data set to experiment. But eventually I had a tough time to just curate the images. Like I was not able to have a proper data set which was only focusing on the one sort of structure, or like it may be just the facades or just the building, and yeah, like just the building. So I mean, like this was the data set which I collected initially, which was around 250 images of the temples in India. And so I will just quickly show the work which I did from this.
Yeah, these can end up being quite large files sometimes.
Yeah, yeah, like my laptop's having a tough time with the huge files. Okay, so I'll just try playing the other data set which I switched to today. So yeah, so for the past 1 year, so especially since the last digital futures workshop, I took part in a workshop with Futurely, and where I was introduced to this procedural modeling using ZBrush, Grasshopper, and Python. So yeah, since last June, I have been doing these models through various exercises, and I also I took part in various workshops since then. So this was a data set which I had already, and I thought that like this was much more well curated images which could turn out to just to be good for the latent work. So like just to show all the data sets which I collected and also augmented using Runjia's script. This was how it turned out. Like this was a total of around 450 images. And like Carlos mentioned, throughout these renders, I had a sort of one particular frame which was either white, black, or gray. So I thought that could be interesting to experiment. So after doing the latent work for this was what I got. Oh no, yeah. So I'll just yeah. This was like what I got after the collab script. So from my original latent work, I just extracted all the JPEG images through the script. Yeah, through the script, and then I had the video made again. So this was how it turned out to be. And I'm also so like while experimenting on this, like what I thought was and also what I plan on doing in future is I'm also planning to build a data set of my own work. So I'll be planning to like just create more of these objects in future, and maybe curate a data set of close to 5,000 objects, or even like something of that. So and just experiment more with colors and forms, and like just see how it turns out to be, because I'm really interested in how the latent work works. So like yeah, this is how it turned out to be. And yeah, that's about it. And yeah, so from the video I managed to extract these images, which I will be using for the stacking in Grasshopper and also the 2.5D output. Yeah, that's about it. Thank you.
Thanks, Neil. And it's really interesting work. I think I guess your and Carlos' work, I guess it brings the idea of in partners, could you possibly look at a final project which begins finding, creating some sort of latent walk or between your projects. But
yeah, sure.
really good work. You want to pass it to the next person?
Yeah. Maybe I'll pass it to Fei. Fei, yeah.
Me? Okay. Yeah, I also don't have like a slide, but I can show what I did for my assignment one. Give me a second. Yeah, so basically what I did for my assignment one is I try to use the machine learning, the style game, to make an image for one of the essay I'm written on the portfolio agency. So I'm very curious on like if, for example, like all the architecture students are making portfolios, and then can like AI also make a kind of similar portfolio. Let's say, because like usually a portfolio agency is kind of teaching students how to make, like if you want to go into a GSD, then they kind of teach you how to do a GSD style portfolio. But then like maybe AI is better at this, like when thinking about like how to imitate like the styles. So I'm still trying to find my folder. Yeah, okay, I found it. So this is the final result of like a portfolio kind of trained by like the style game, like using more than 1,000 images from the portfolio issue online, mostly GSD portfolios actually. But yeah, like the result looks pretty, let's say, GSD portfolio-like. I mean, like if I feel like if I can like use more portfolios, like let's say like if I can increase the number of the portfolio I use, I think in the end I will lead into like a pretty good results that might be able to use to apply to GSD in the end. Yeah, for the later projects, like the collaboration right now in a group with Carlos, like we are working on like basically gathering towers informations. So like because towers are essentially like, oh, I'm not sharing screens. Oh, anyway, yeah, towers are essentially like shape-driven designs. So which we thought this is kind of pretty good fit for a 3D game, and then we just find like hundreds of like the famous towers, like so. But yeah, it's still in the process. So that's what we are going to work on.
Thanks,
and
super interesting.
I point to another who has not gone yet?
We're gonna give another 5 or so minutes, so maybe we can get 2 more people. And please, everyone, do use the work sharing channel. It's always great to share your work, but maybe 2 more. Who was that? That you nominated?
Do I try ping someone?
Sure.
Maybe Peiwei.
If anyone feels like sharing, do feel free to jump in. Sandy, Lisa,
Hi, I can go next. Let me just try and share my screen. How does that work? Sorry, I'm generally not bad at this. Yeah, I'm having trouble sharing my screen. If someone wants to go next, that's fine. I'll try to figure this out.
Alawia or Ira, Isa, Payway.
Yeah, I've done something, so maybe I could show, but not as good, because I feel like it's a bit overwhelming for me as a like introduction to AI and machine learning. But I'm gonna give it a go. So I'm gonna share my screen. Can you see my screen?
Not quite, actually.
Okay. Wait. Okay, can you see now what I'm showing?
Not quite yet, actually. So you click screen share on the bottom and then you select a screen, or
yeah, the screen, but it's not showing anything.
Then you press
share. Wait, share. Okay.
Share, yeah.
Can you see now?
Perfect.
Yeah, so from the beginning of the workshop, so I looked onto plans. So I started to explore plan is my data set. So I took around, how many are these? 100 of them, which I kind of mixed up, like the lobby ones, the traditional, for example, architecture from the Gulf and so on, just to see what I would get from it. And I went to Runway. Can you see the screen? Yep. So I generated, I think I got the results, but I think I could improve more by maybe, making all the images more high resolution and the size, great. So I pretty much got it, and I generated the video, but I think it's not giving a clear result. You see my screen?
Yeah.
Yep. Sorry. So I'm trying right now to get them more HD, make them all same size to improve it. So until now, yeah, I'm just trying to improve on this and continue to catch up with the other day 2 workshops. So yeah, that's pretty much from my side. So any tips would be great.
Yeah, thanks so much. I mean, you can almost start seeing some of that pre-trained the faces kind of emerging there. So you can appreciate how the more steps you run the model for, the more.
Yeah, I ran it around 3,000 as suggested. So yeah, pretty much I'll improve on it.
Another tip that I think, I would like to say is that probably for your floor plan, since the convolution layers process the local patches of your images, so it will be easier to get the results if you color all of your pochets in the black color, like color all your walls black, and then it will be greatly improve your training results. So if your walls are white, then sometimes you just not differentiate well whether it's wall or like the background. Yeah.
Okay.
Have you used the augmentation as well?
Augmentation as in
because the benefit of using a plan is that you can rotate it and mirror it any way.
No, I just took the images and just use it as let's go first try. Let's do this. Yeah.
Okay.
Yeah.
How many images did you run?
I run around 100 100 images. I should increase more for better result. That's my goal. But I was trying it the first time. So
Cool. If you do want to use the augmentation notebook in Colab, you can use the 100, put those in, and it will rotate and mirror them. So you don't have to actually download or get any more than 100 is plenty actually.
Oh, okay. Where do I get that augmentation?
In the toolkit folder.
Toolkit.
In the Dropbox. In the Dropbox folder.
Oh yeah, in day one. So 04 toolkit day one, and then there's you can use the 2D style again, the processing. And if you go to the recording again for on the YouTube channel, you can also see us running it. Well, it looks great.
Sure, thank you.
Thanks.
Great. I guess we can just keep going with the lecture because we have like quite a limited time. But yes, thanks all for all the great presentation. It's really amazing to see how much progress you have made like in such a short amount of time. And yeah, maybe one suggestion that I just think about is like if you have like a facade instead of like a plan that you want to use for the 2.5D workflow, you might want to consider just to use a horizontal. Oh yeah, okay. We have another like self-photo for presentation. Yeah, go ahead, send it. And you can use a horizontal stack of images instead of like a vertical one, which makes more sense in terms of spatial relationships. Yeah.
Sorry, just a second. Almost got it. Oh, yeah, I don't think it's working. I don't know. Yeah, sure. Can you see my screen now? I guess.
Yeah.
Cool. So yeah, I did collect some images for Japanese shrines and temples, and it was around like 160 images, ran for 3,000 steps. And the latent space walk was pretty interesting. One thing which I'd noticed, which was also peculiar, is that these trees, they kind of appear and disappear with the images. Maybe I should have segmented them out to capture the architecture well. And you can see that one of the things which I noticed, which was also pretty interesting, is that the dome shape on the top, I'm not sure if that's the right word for it, but like you can see that the architecture, like the latent walk, is trying to figure it out whether it's working or not. And this was pretty interesting for me as like a starting experiment. So yeah. And I didn't have time to finish up the 2.5D walk model yet, but once I have, I'll probably post it and share it.
Thanks for that. I really think the natural element really gives it, this mix match between the two really creates some odd but interesting results.
Yeah. Also, if you're using 2.5D, you can also try to extract different pixel values for different layers, and just maybe for one object, for one layer, you extract the tempo pixel using the red color, and on the other hand, you can also extract your plants and use that as another layer of objects in your visualization process.
Yeah, that's a pretty good idea. Thank you for that.
Yeah. I think our workflow is pretty much very flexible, and you can customize it according to whichever representation you want.
Yeah.
Yeah. All right. Is there anyone else who really want to share their work? All right. Yeah. If not, I'm just going on with the lecture today, and yeah, I was originally planning to give like a really quick section about the convolution and how like the mathematics works if you want to try to implement a convolutional neural network or a generative adversarial network in the PyTorch library. But I think due to the limited amount of time, it's actually definitely like an optional choice. But feel free to explore all those tutorials on the pytorch.org. And the PyTorch is like an open source free libraries for deep learnings, and you can use it. You can just basically try out all these tutorials to use or to customize your own neural networks for deep learning. So yeah, I just originally prepared like two very simple slides. The first one is the NumPy basics, which teaches you about like the how the matrix works in the PyTorch, and basically deep learning is all about like matrix calculation, and you represent your images as a matrix of 3 channels. Each of them is a 2D matrix. And since their images are in the RGB format, so we have R channel, G channel, B channel. Each of them is like, for example, we have a 2.56 by 2.56 pixel image. And then you have like each of the matrix is like 2.56 by 2.56, so by 256. And you have 3 channels stacked together. That becomes a 256 by 3 matrix. And you use that for all those 2D convolutional neural networks for just the processing. Yeah, but and also there's like how you can just customize your neural network. I'll just really quickly go through the those libraries, so you can just probably try out them after class, and I'm gonna share all the contents with you just later. Yeah, so basically it's what is a brief intro is that what it's doing is just trying to simulate like a function, which is the polynomial function, like y equals to a plus bx plus c plus x squared plus d plus x third square, and they generate like a series of data using like a sine function. So you basically have a sine function, and you're trying to sample this distribution of sine function using the neural networks. So you can understand neural networks as a complicated function that takes like a matrix input and export and output like another complicated matrix. The shape of the matrix could be different depending on what type of task that you're doing. So, but the fundamental element is the matrix calculation. So this one just introduces you how like get a basic understanding of how the matrix works, and the second tutorial is how you use this matrix calculation to actually create a neural networks of your own choice. And you're going to write all these functions by yourself using the provided APIs by PyTorch. And it's pretty fun. And they have like a very detailed get through of how you can actually do each of the steps. So I will not be going through those like today, but feel free to ask me if you have any questions about this tool. It's like an advanced version of tutorial that you can have. So for understanding the how the basics and techniques that you're going to be acquired for doing deep learning research. All right, so we're going to then jump into the second part of today's lecture, which is I think is also like quite interesting about the shaders and visualization in computer graphics. So yeah, so one starting point that we're going to have for today's lecture is that we start with the question that how you visualize the 3D objects on your computer screen using the modern computer graphics pipeline. So basically what you do is you use like, it's like a camera process. Like you have all those 3D objects inside some of the 3D space, either represented by mesh or voxel or other representations such as the B-reps in Rhino, or like even using procedural language such as CSG, or which is representing the solid constructive solid geometry, or the CGA language, which is the language that the procedural grammar that they use for generating cities inside the city engine. So whichever representation you use, you're gonna have a 3D space inside your computer world. And how you're just gonna project that onto the screen is by using a camera. So computer graphics is actually the camera for display your virtual 3D objects onto a 2D screen. But you can, because it's a computer, it's like a advanced DSLR camera. You can not only adjust the default parameters like a camera, like the camera lens, focal length, or like the camera's, just the focus of the camera, as well like how you want to like filter out different parts of the images. you can also customize many other elements, such as adding like filters to your image, or even do some like adding like some pixelated effects or some very interesting like electronic visual effects to your the images that are going to render on your screen. So I would say that shaders are quite important in terms of especially in the gaming effects industry. Like you can create like a lot of like post-processing like fires or other like physical simulation visualizations using the shader pipelines. So, but basically we're gonna introduce briefly how the different parts of the camera works, because we're gonna actually customize how we're gonna render our objects in Rhino using this workflow of CG pipeline. So first of all, we start with our representation in 3D. So whichever format you use, you're gonna end up with the mesh, because most of the graphics card companies use like the mesh representation for rendering objects. That limits like actually the representation of your systems, because like it's essentially the end of how you're gonna render your scene. So basically, you start with like a mesh, as you can see here. So imagine this is composed of like thousands of like mini triangles inside the mesh services. I'm not gonna draw the triangle, but you can imagine each of the quad as a small triangle. Yeah, as you can see in the second picture, like each of this is a small triangle in your mesh. And if you zoom in to the small triangle, how the graphics your GPU renders 3D objects, it renders a mesh is by rendering each of the triangle. And they're gonna use the same shader for each of the triangle because it's like a parallel process. So you have the same format for all the triangles. All you need to do is just you compute them using the same formula at the same time, and it'll be vastly very efficient compared to the CPU, which can do only like the single-threaded processing in most times. So once you have the triangle, it's still like a conceptual triangle. How can we just change the conceptual triangle into an actual image pixel? So that's where shader comes into play. So what shader does is that the triangle actually also does not exist in computer. What it does is the point, the 3D coordinates of the 3 points in your triangle. So you have the coordinates of the 3 points, and for each of the points, you're gonna remember some of the attributes of the points. So for example, it's X position, it's Y position, it's Z position, as well as the RGB values that you want to display on this triangle. Yeah, so the vertex shader are gonna take this information from your model to the shader, and the shader is like the formula to tell the computer how you're gonna display the object. So you can display only the dots. Like we only want the vertices of the object without any interior. Then that's it. If you can also draw that as a line, just a triangle with just 3 lines. If we Rhino wireframe, that's how it renders as a just only displaying the line elements. And you can also, for example, draw inside your screen, inside your triangle, using some interpolation techniques. So for example, if I want this to be red, this triangle to be red, and this point to be yellow, and this point to be green, then the color inside will be just like a natural interpolation of the 3 colors. And they're gonna just merge into each other in the middle. So that's how you define, that's how the graphics, that's how vertex shader defines how do you interpolate how render your geometry elements. And those information will be will be also passed on to the second shader, which actually takes charges of converting your triangle to a screen. So basically, we still have the notion of the triangle here in this image, but with the RGB value on 3 of the vertices, you're going to determine how you interpolate the colors inside the triangle, and your image sampler samples the point or inside your triangle, and depending on the distance to the three point in your triangle, it will calculate what the pixel value is based on some of the formula you define in the fragment shader. So the fragment shader actually determines the rendering pattern of your inside texture, while vertex shader is something like more similar to how you're gonna display your triangle vertices and the structure of your display images. So that's like a quick overview of how the entire workflow works. And after you pixelize all the images, it will just send out to the screen for display. Wait a second. So yeah, this is like a typical data structure for how the vertex, how the data is passed to vertex shader. So basically, for each of the vertex, you have some information stored in the vertex, and that's why we call it vertex shader. And this is another visualization of how vertex and fragment shader works. So basically, we map this triangle to the screen space by doing some crazy coordinate transformations, projecting the 3D objects to 2D, and then we back project the pixel to the 3D world to sample the color of the each of the point. So these are some of the shader effects that you can see out there in the web. Like the shader toy is like a really cool platform that has a lot of like shader effects that you can play with. And also this is also rendering only by shader. It's not using any textures. So you can see that it's already performing very efficiently and like having some really amazing physical renderings in terms of like performance. It's instant, almost real time. There's no delay. It's not like a rendering according to physics laws, but it's just visually trying to change by visually changing your camera, computational, like mechanics, you can already achieve some really cool visual effects. And this is another example using like a marching volume. Marching volume algorithm. So all the geometry inside this video is procedurally generated without a single 3D model, using only shaders. So shaders are pretty powerful techniques that in computer graphics that I think could be really beneficial for the visualization of architecture projects as well. But shaders, they have always existed in like a painful way, like in the either in Unity or like Unreal or other CG domains, but they have not really come into the workflow of architects. But thanks to McNeil version 7, we now have the GHGL, which is a shader toolkit that you can play with in Grasshopper. And you can computationally control each of the vertex in the Grasshopper using this simple library, and it's pretty powerful, I would say. So next, we're gonna explore some of the simple shader effects in GHGL library. Yeah, I'm gonna do some like real-time demos using this workflow. So first, you make sure you have the Rhino 7 installed on your computer. And in order to install the GHGL, you're gonna click into package manager of your Rhino 7. And you're gonna search GHGL inside your package manager, and you install it, and you restart your Rhino in order to use it. And then that's it. So once you have your, once you have your like GHGL installed in your computer, we have some example file that you can play with inside the Day3 Toolkits repository. For example, the GHGL, and it has a lot of like sample files and tests that you can use to just learn how basically shaders work. And you're gonna write your own shader in the GHGL language. But I'm just gonna quickly show some of the workflow that we'll be using that are integrated with the 2D image generation process. So here is one of the here's one of the sample files provided by Rhino. So essentially, what it's doing is just as you can see, this is like a BREP. You can pick it. It's just like the Rhino logo. Oops. It's just like the default Rhino logo, and it's gonna color the Rhino logo based on the type of shader that you customize. Yeah, so what this does is nothing special, but it's, you see in the vertex shader, it's just a pretty standard. And to actually use the shader file, so you have to use mesh shader, GL mesh shader. So that's once you install the library, it's gonna appear, and you're gonna plug your mesh to this component. It's like a customizable interface where you can actually add input elements as much as you want. So here in the interface, you can just add different elements. Yep, and once you click into it, it will came up with this like GL shader interface here. You actually write the GLSL code here to customize your shader. It's a bit of like a pain to explain how GHGL works because there's all this type of like computer graphics knowledge behind it. But basically, yeah, just like you can say that the vertex is actually refers to the vertex shader that are going to use for rendering the mesh. And this fragment is actually the fragment shader that are going to use for rendering the mesh. And the GLSL language, so it's a kind of different, so let's use a scribble for this. So yeah, here we have to differentiate the concept. So yeah, let's say that the GHGL is actually refers to this library, the one developed by Grasshopper. But the syntax that this GL is using is actually called GLSL. So it's pretty a similar language as the C. That's C. Just you declare variables in a very old-fashioned manner, like layout function. It's like importing some of the existing parameters that are embedded in Rhino. So Rhino provides those APIs for you, and you can also import those built-in variables by using the built-in uniforms. Such as the camera to clip coordinates or the built-in like mesh texture coordinates. Mesh texture coordinates is what you're gonna use for rendering your mesh. It's like extra like texture that you're gonna import from your local directory. So for this, the fragment shader is doing nothing but first calculating the distance to your camera. And based on its distance to your camera, so it's just changing the color, you know, of each of the vertex that you're going to render on your screen. And what it outputs is the frag color. So it's basically like a vec4, means that it looks like a vec4 is actually what looks like. It has 4 values. It's a 4x1 shape vector. Vector 3 is like VTP, so vector 4 is to be VTPQ or things like that. All right. So if you do nothing to the mesh, you know, just customization, it's just gonna render nothing. And oops, this is like the first examples. There's also other examples that you can play with. For example, like the post-processing effects, like old TV in Rhino, and this could be really cool. Like, you know, if you're rendering something like in certain styles, and you see that it's animated real time, so it's pretty efficient. Also another example regarding how you can color your mesh using this like a linear gradient of, yeah, it's pretty similar to that concept of like doing some simulation, you just do the similar thing. But this is pretty much vertex color based. So you can just connect your color options based on like the inputs of Grasshopper. For example, there's some of the Rhino lines and points and some of the space 3D coordinates of those objects, and use them to render your mesh vertex. So basically, like if you bake your mesh, oh, it's a BREP. All right. So we're gonna display how that works. But if you bake your BREP, and you know how that works. You have to use a mesh, convert that to a mesh, and do the same thing here. Okay. Now you bake your mesh, and as you can see, let's change to another mode to check it. As you can see now, and each of the object on your mesh is essentially a small triangle in Rhino. So yeah, what it does, that's completely unwild the entire mesh. Just do the exploration. Or it's going to be taking a long time, but you can see that each of the surface is either a quad, which is like a composed of two triangles, but essentially they're the same because the quad can always be exploded into two triangles. Yeah, so it's essentially rendering each of the triangle color based on its adjacency to the to the point on this, like the line that you define. Yeah, so that's how this shader works. So now we're gonna after some like simple tutorials about about this one, we're gonna jump then into how we do the post-processing for our project. Here we go. So Grasshopper. So yeah, we're gonna first look some of the visualization techniques that are gonna be used for the 3D GAN. So after you train your model, you're gonna serialize your model to your like Google Drive directory, and so this is where I put my g.pth file. So that's in my Google Drive, and here's another OBJ path where you want to store your 3D models. So let me see whether I can do it. Okay, so if you import your model and run these cells right after the run inference on model, we're gonna like use our model in the inference mode where it's just gonna generate a 3D latent block for us. So how are we gonna do that? So what a 3D GAN neural networks structure that we're using is essentially the same as the one from like the original MIT paper, learning a probabilistic 3D representation for 3D objects. So what it does is basically take in a random vector of just noise of 200 numbers, and it's just gonna pass the vector through the 3D GAN networks. And once you have the results, you're gonna get a NumPy array. So we can print, just whatever Z looks like, and also print whatever the prediction looks like. So I'm gonna do this and result. Oops. Now, and this is like the noise vector. All right, let's take a look at how that looks. Oops. So the Z is essentially like a 200 by 1 long vector, 1D. And the output like is actually a 3D object voxel. So, and this is like the visualization of the voxel that it predicts. I'm training this on a stair dataset. Unfortunately, it doesn't converge because the stairs are just really hard to learn. So yeah, but the chairs gets a really good performance. Sorry, we can just try this instead. So we have 3D GAN chairs. Sorry, to change the mode, I just forget the name of the 3D GAN chair 64 and the folder name and not this. But anyway, yeah, whatever. Once you have the models like imported in your in your training, sorry, it's this one. So you can just do the visualization here. So let's just print out the shape of the tensors. So essentially, each of the thing that you can get, it's like a tensor of some shape. Either it's like a noise, which you use for the latent walk, or it's like a voxel. Now it's much better. Like we can see that the noise vector is a torch tensor of size 201. And the result of our inference is a tensor of result 64 by 64 by 64. So once we have this, like it means that each of the point is like a probabilistic like value of whether this point is going to be likely to have a voxel in that point. If that's larger than 0.5, it means that it's very likely to be a voxel. If not, it means that it's a void or like nothing there. So using this technique, we can transform this into a Boolean representation of value 1, 0 of your prediction results. So for example, we can just slice, just to give me like, you know, maybe the first element or maybe the first line in the training. Sorry, just slice that in the wrong way. Sorry, I've been done this for a long time. Yeah, so as you can see, this is one layer of our training results. So it has some like true values, which means that it's going to be like a voxel, and have a lot of false values, which means that it's a void. And you can use the utils.plot matching field functions for plotting the mesh representation temporarily. And then we're gonna create another workflow for generate a PLI file, which we're gonna use for visualization in Grasshopper. So what we do, we just you can run this file and you can see that. All right, just whatever. I just changed some of the code yesterday. So if you run this code, you're gonna see that you have this point PLI file somewhere here in your data directory, and you can import this PLI file into your into Rhinoceros. Yeah, and if you run this like more complicated generates 3D latent walk is essentially a Python generator, which is similar to something that throws the results to you. So if you run this cell, it will just and you can set the obj path, which is the the final output path that I'm having for like storing my generated results. Then you are very likely to have wait a second. Yeah, I think I defined this obj path before. Okay, so that's in the output 3D GANs. There are 64 objects. The drive, my drive, DF, output 3D GANs. There are 64 and objects. So this folder contains all the PLI file that you're going to be used for this like visualization. Oh, sorry. I think there should be like there could be like a mistake. I'll just debugging the code a little bit time later, but it's essentially containing all the PLI files that you can generate out of the 3D GAN. Yeah, now it's coming. Yeah, like all those PLI files. You can download them. So it is, and you can import those PLI files into Rhino. Okay, this is like the results that are generated from the previous plot matching cube. But if you download the entire PLY folder, sorry, it's gonna be. Okay, it's gonna be in this like you can download the entire folder that contains all the PLY files and visualize them, in Grasshopper and import them and using the import function that we provided yesterday. Yeah, so this is like the actual PLY file that I generated. So you import them to Rhino, close the Grasshopper temporarily. You can see that we have a 1-point cloud editor selection. I can zoom into it. So this is the shared data set that I'm having. So essentially, it's like a point cloud objects that are get serialized. All them to make them like a cloud of points. Yeah, and using those using the generator plot PLY, we can get a continuous representation of the 3D point clouds. So now that we have this, yeah, the next step that we're going to do is the yeah. So this is essentially the same thing that we did yesterday, like importing all the PLY files, and I can perform like a really quick visualization of the results. Okay. So it's essentially just importing everything from your directory. And you can change the sliders in whichever fits your dataset number. Yeah, and that's pretty much like how you're going to do the shape interpolation using this sequence. Yeah, I'm scrolling that really scrolling that really fast, and there's some domain mapping issue. So if you change it like this, you can see that there's like a continuous shape interpolation for those point clouds in the 3D setting. But do not do this real-time visualization directly with your mesh, because it's just going to crash your computer. This like mesh voxelization is very slow. Just so do not. Oh, I have placed a data dam between those real-time elements and those that you cannot actually run real-time. Okay, but the thing is essentially the same. So we have the data points, and we perform like a voxelization as we did yesterday. And they report the everything and perform some reduce reduce of the mesh, and you can do some like manipulations of visualization, such as like rotating that around a certain axis, or you can give it a color using the shader technique that we're doing today. So I'm combining this shader with the 2D workflow that we 2D generative images from the first day's workshop. So what it does is that I just grabbed a bunch of like matchcat images, which we use for rendering, and perform this kind of like style transfer using the style transfer techniques in Runway, and get those like images for rendering the objects. Here again, there are some elements that you can play with one by one. The first one is a very vanilla mesh visualization with the GHGL. The second one is just you can change the RGB color of your mesh by playing with this like sliders. It's essentially the same as you're rendering, you're using the vanilla mesh rendering. But things gets a little bit advanced by using the shading function. As you can see, we can apply those 2D images onto our mesh, using the latest GHGL shading. It's essentially performing some flat shading on each of the triangle in your mesh. By performing first, you're gonna create a varying variable called texture coordinates, which is the one that we use, the variable that we use to pass from vertex shader to a fragment shader. And then we import that varying variable in fragment shader and use that to generate a texture 2D based on your input texture and your UV mapping of your mesh. Unfortunately, the texture mapping of your mesh is not working correctly in Rhino because of they're not performing any support to vanilla mesh, but instead they're just only supporting their BREP representations. So we cannot do any texture offset now in the Rhino, but this flat shading visualization is already, like, I think, pretty good enough, for the sake of the workshop. And you can also play with, whichever texture that you want to render here. You can also see that this one also changes. Sorry, disconnected. Side. Okay, this is the correct one. So you can see we can have this like a bunch of the images here, and you can choose the one that that are good for your visualization. Okay, let's just preview this off. So what's more, just like we did for the just a rendering workflow, you can also use like a number of scalar to scale your mesh rendering. For example, like if we multiply the texture shading UV by the scale, then we can just scale our texture coordinates. As you can see, it's becoming really small, and now it's like really huge. So you can play with this, just trying to get different effects inside the grasshopper visualization. And what's even cooler is that you can also performing some shift effects based on time. So for example, if you keep like a shift element, so basically what you do is nothing but just adding a time plus the shift variable to the UV mapping of your mesh, and then that's the color is going to be shifted along the x-axis every delta time, that time by your shift. So you can adjust the speed of the shift, and it looks pretty, pretty neat, like this. And you can capture some really good videos out of this. Like for example, we can do, this is like really fast shifting effect, and here's some like really slow shifting effects. And you can also mix the shading effects with some like filter or other two different textures together by using the mix function provided by Rhino, the GHGL functions. So basically, it's very simple, just mixing the first color and the second color with a weight, but both of them have to be a vector 4 in order to do that. Then you can just add different color tunes to your objects to just fine tune the effects. You can also add different textures together just to gain a mixture of two different latent images that are overlaid onto your latent object. Okay, so this is pretty much like this part of the visualization workflow that we're going to use. So this is the post-processing script. The last script that we're going to introduce today is nothing too different from the post-processing script, but it is just like a simplified or efficient way if you want to get a quick visualization of how the 3D objects, how the 3D latent work and the 2D latent work can work together. So as we just showed in the previous one, you can preferably generate a series of images and a series of objects. But can you apply the series of images to the series of objects as materials? So this one, the animate just do this part for you. So essentially what we do is that we use the same slider to control this enumeration of the image and the objects in two different folder directories. So the first folder directory, I use the cloud GAN to generate a latent walk of like sampling the images from one of the cloud GANs on Runway. Yep, here. As you can see, this is essentially like a latent image walk. And you can see the material is continuous. And you can use this continuous material to apply to your mesh, where your mesh is also a continuous latent walk. So you just replace this one with your continuous image directory, and this one with your continuous 3D object directory. And to generate a image sequence, or further we can post-process to a video using FMPEG, you just use the, just right-click on your slider and use animate, and you can, just probably create a new folder in your desktop, like animations. Oops, failed to rename. It's just consuming too much memory from my side, but all right, we're gonna put in a folder 4, and you can set the perspective that you want. It's actually capturing the rendering in your Rhino window, and you can also set the definition. We're gonna set a really small one just to get a feeling of how this works. You're gonna generate 10 images out of this workflow. So we're gonna make our setup, and press OK. Then you can see the slider will be automatically, changed in this sense. Sorry, this might not be working so well because it's just working through. I will just use like probably 30 images then. Oh. And use a different slider like 30 for the visualization, which is gonna be incremental by 1. All right, I'm gonna set this to do. And start our animation process. Yeah, as you can see, it's just gradually begin to interpolate your images depending on the frame number that we set. Can also make it more like delicate by just make it larger, like for 30 steps for 30 objects. Yeah, and do the animation again. Then it's going to increment by 1 each time. And it's essentially just trying to capture the latent walk of your images if you make the numbers really large. So I'm just going to show you some of the results that immediate results that I'm having. So it's here. Yeah, this is like the latent walk 2D plus 3D that I generated using this workflow. So essentially, I maybe have reduced the mesh too much that you cannot see the feeling of the similarity between the objects. But if you have if you do not reduce your mesh too much for the sake of visualization, you can feel the continuous of both your 3D shapes as well as the texture on your 3D models using this workflow. Yeah. That's pretty much, I think, pretty much all of the hands-on parts for today. And it's playing slow, but essentially, you can see that both the texture and your object is just changing continuously based on your image. And this is essentially the chair dataset that I'm using for the object generation. And in the last part of today's lecture, I'm just going to cover some of the neural procedural modeling, more advanced, like neural modeling techniques that are different from the voxel representations. So as we all know, there are all different varieties of representation for 3D models. So we are using voxel for this task, the beamvox. There's also a lot of like those files, other types of representations out there, such as the point cloud, which use a PLY representation that we just used. It's more compact than the voxel representation. And because it only remembers the points in your game object, but you do not have any context of how large the point cloud is, or how large your voxel is. You will transfer the point cloud back to your voxel. And there's also like the most commonly used mesh representations, such as OBJ, OFF, SKPF, FEX, STL, Collada, GLTF, and DAE. And those are just common mesh objects and are very GPU friendly. And we have also BREP for Rhino 3D, G-code for 3D printers, and other domain-specific languages for neural procedural modeling, such as the CSC, Revit, ABC, and CTA, which are generated based on like a procedural language or grammar for 3D modeling. So why is 3D modeling using procedural grammar important? So those procedural modeling is generally the way that we refer to this. So it's like you essentially built upon the idea of shape grammar, where you generate objects using like a series of text or a series of like a language based on certain grammar that you define. For example, the wall AB defines a wall in position AB. And this is the CD Engine paper that I referred to. Sorry, I forgot to put the bibliography, but it's like the paper called the procedural generation of buildings. So you use this like procedural grammar to generate a city using city engine, using this type of grammar language. And you can see we have this language for the generation of the 3D objects. And more recently, we have this, sorry, I forgot to put the bibliography for this as well. It's called inverse CSG. So what it does is that it's trying to create a neural program executor to generate 3D shapes by learning the CSG grammar, which is a procedural grammar for generating 3D objects. So this is like also CSG is very similar to other procedural modeling grammars, such as this has the syntax of generating both primitive shapes such as square, cylinder, circle, lines, and the relationship between the different primitives. And you can use a powerful language model, such as the step LSTM, for learning a probabilistic distribution of how the objects are generated using the grammar. So as the language models becoming more and more powerful, it might get easier for us to learn some of the patterns of generating or assembling 3D objects using certain grammars. So that's why this is important. And because the grammar is another level of abstraction where both human and machine can understand. And it makes sense for generating 3D shapes from those like language models instead of like just using the 3D representations themselves. Actually, mesh and like BREP and voxel, to my opinion, is not human intuitive because you cannot just understand directly how a mesh is manipulated or works. But if you're using a procedural grammar, then you can immediately have a concept of how the things are assembled. For example, this is one of the papers from the CCL, CCL computer graphics groups, which learn a assembly of robots that are best for certain tasks, such as walking up a stair or walking inside a labyrinth. So based on the procedural grammar of assembling a robot using the input components, as well as like certain possible connections between those input components. So this is trying to sample a optimum strategy of grammar out of the distribution of the performance space by testing the robots on those input terrains. So this is like a pretty interesting topic that I would like to quote. Sorry, I forgot to put the bibliography again, but it's like using reinforcement learning and graph heuristic search, which is an upgraded version for multi-color tree search, the algorithm that the AlphaGo was used. So this is essentially trying to use shape grammar for generating objects, depending on the performance captured by robots. So we can, let's just, as I said in the first day's lecture, we can use this type of reinforcement learning algorithm to sample like language pattern from the 3D modeling world and test it and simulate the performance on like a game engine or other differentiable physics machines. And then we can get a really powerful policy network that can generate complicated objects based on the procedural grammar that are defined coherently by human and machine. So that's all of my lecture and workshop today. So yeah, I'm gonna stay here, see if you have any problems for running the 3D again. Yeah, and happy to take any questions from now. That's it. So does anyone have any immediate questions about the contents of today's lecture? Oh yeah, Dora, go ahead. Yeah.
Yeah. Hi. So I think the lecture was great. So I have learned so many things. But I can't work with Colab. It creates problems for me. I don't know why. So what should I do? I'm just want to ask this
Okay. No worries. I'll just think class is over now, so I'm gonna stay here for like maybe extra like hours, like 30 minutes or so. I think George also have announcement afterwards. So after maybe George's announcement, we can just handle just troubleshooting everything that you have for with Colab. I know it's not easy because it's like essentially what like computer scientists used in a daily basis. Yeah, but I'll be staying here for a while. Yeah.
Yeah, sorry. Thank you.
Yeah, no worries.
Maybe thanks so much, Runja. That was really interesting. Maybe I'll share a few last slides relating to the next few days, and we can definitely stay after the time is up.